Hi, my name is James Kelly, and this is my overview of Lab 2, the effective drag force on an object falling. Introduction. The purpose of this lab is to create one observed and two computational models with the motion of an object falling straight down, and drawing conclusions about which forces are acting on it. The observed model is created with a video of a notebook falling, put through a software which will track the change in position over time. The computational models are based on a program that iteratively changes position over time based on a velocity affected first by only gravity, and second by both gravity and drag. The primary physics principles of this lab are position, velocity, net force, gravity, drag, and Newton's second law. The main results of this experiment are the differences between the first computational model and the observed slash second computational model definitively proves there are multiple forces at work, mainly both gravity and drag. Now I'll explain the main physics principles in more detail. Position is a vector quantity describing where an object is currently in space. Velocity is a vector quantity describing the change of position over time. Gravity is a force that pulls an object in the direction of another object of mass. The magnitude of gravity on Earth is expressed as m times g, directed in the negative y direction, where m is the mass of an object and g is the gravitational constant on Earth. Drag is a force that pulls an object in the opposite direction of its current velocity. The magnitude of drag is expressed as b times velocity squared, where b is the drag coefficient of the object and v is the current speed of the object. Net force is the summation of all the forces acting on an object, usually expressed as a vector. Newton's second law describes how the net force affects change of velocity of an object, which is mainly characterized by the following equation. Net force equals mass times change of velocity over change time. This can be rearranged into several different derivations, such as the position or velocity update formula, which are R final equals R initial plus V average delta t, and V final equals V initial plus F net over M delta t. Data. The software used to obtain the observed results analyzed the position of the notebook in the video over time as it moved rightward in the video, which was oriented in the negative y direction. The software then recorded the position at different frames based on time elapsed, the scale established, the tape measure in the video background, and a set of axes established at the notebook's starting point, which is considered to be 0, 0. It then created a graph based on the observations which shows the effect on position over time. This model is chosen because it represents the specific observed result of the experiment. Axes were oriented so that the direction of motion was on the y-axis, even though in the video it was technically moving rightward. Computational models. The computational models were created using two different Python programs. The iterations it uses are calculated with the velocity update formula and then the position update formula, applied using a uniform change in time. The program then graphs a change in position and a 3D model of the predicted motion. The first program assumes there is only one force acting on the object, gravity. The second program applies both gravity and an additional force, drag. The program sums these two forces and uses that as the net force as used in the velocity update formula. Here are the two codes. The left is the force of just gravity, and the right is the force of gravity and drag. Conditions of the experiment. The initial condition is a notebook at rest with a position of 0, 0 and an initial velocity of 0, 0. The initial time of the motion in the video is t equals 0.277 seconds, and this is reflected in all data models. The system is the notebook, and the surroundings of the universe around the notebook. For the first computational model, it is assumed that the only net force acting on the notebook is gravity. For the second, it is assumed both gravity and drag are acting on the notebook. These assumptions are made to clearly distinguish them from each other, and see which model more closely matches with the observed data of the notebook falling. Discussion. Observed data versus computational models graph. This is a comprehensive graph showing the results of each model. Each model has a similar velocity as well as identical starting position. There is a key difference, mainly in that the computational model that only takes into account gravity actually traveled further than the two other models. This leads to a definitive conclusion about which model should be accepted as most accurate, which will be explained later. There are some possible sources of error. One possible source of error is the camera shaking. The camera was just held by a person, and it's very possible that it's going to move slightly throughout the recording. This affects the tracking software because if the camera moved in the direction of the movement of the notebook, it would have caused an increase in speed from the perspective of the software, even though there was not. One additional source of error could be the fact that the tape measure used to establish scale in software was in the US measurement system. Although conversion was done from 1 meter to inches, this was not exact. Because the scale was used to establish change of position over time, it could mean it has a small impact on the true distance traveled by the notebook as it fell. Conclusions. Overall conclusions. Based on the distance traveled and the slope of the graphs over time, it can be concluded that the computational model, which includes both gravity and drag in the net force, is the best prediction of downward motion. This result makes perfect sense, as the effect of drag on an object falling is an inevitability. Thus, we conclude that in the recorded video, the effects of both gravity and drag were observed. What does it mean? When considering the two different computational models, the model that considers the force of gravity and the force of drag represents a model which attains a terminal velocity. This occurs because as the object continues to accelerate downwards, its speed increases. As a result of the formula of drag force, this force increases as well. Eventually, the speed will be so great that it causes the drag force to be as strong as the force of gravity, canceling it out entirely. This means there is a net force of 0 and the velocity will no longer increase, which is what it means when it reaches terminal velocity. Also, the question may be asked, what if the notebook was thrown instead of dropped? Well, in this case, the terminal velocity would be exactly the same, as it would just have been reached faster. Even if it was thrown with a higher velocity than its terminal velocity, the drag force would be temporarily stronger than the force of gravity due to the higher speed, and thus decrease the velocity until it balances out again. This means the terminal velocity is the same no matter the starting velocity.